Today we're going to talk about exponential functions. So you've seen these before, probably in Algebra 2, so most of this is review, but we're probably going to treat it a little bit more seriously than you've seen in the past. So what is an exponential function? There's a few different definitions. The one definition that I like the most is a formulaic one. An exponential function, here's the definition. An exponential function is one of the form y equals ab to the x. And that's basically it. Technically, I should say that b should be a positive number. If b is a negative number, then this is a really crazy and messed up function. We don't want to think about that, or at least you probably don't want to. This is a formulaic definition of what an exponential function is. I'd say maybe more intuitively, an exponential function is just a function where the x is stuck inside of an exponent, like it is here. The x is in the exponent of the b. So just a couple of things, we should sort of say what these a and b values represent in any particular exponential function. I'm going to say that a is the initial or beginning value, and I'll sort of explain why that is in a moment. And b is what I call the multiplier, although probably most people would use the word base. They would call this thing the base. Okay, so just very quickly, why is it that a is the so-called initial value and why is b the multiplier? To see why, let's just take an example. Consider the exponential function y equals, 2 times 3 to the x. Okay. Now, very often in applications, exponential functions are used to model some process which is happening over time. Very often, the x represents, so the x variable often represents time. Not always, but it very often does represent time. Now, if we want to think about the beginning value of the function at the very beginning, when the clock just starts ticking, what x value would give you the beginning value of the function? In other words, if you're talking about the very beginning, when the clock just starts ticking, what would the value of x be? It would be 0. Okay, if no time has elapsed, then x should be 0. So the beginning value, okay, the value of the function right at the beginning will be obtained by replacing x with 0. So let's do that. I have y is equal to 2 times 3 to the 0. And then what we have to recognize is that 3 to the 0 is just 1. So this is 2 times 1, which is 2. Notice that that is exactly the value sitting right here. That is exactly a in this exponential function. You can see, hopefully, why we call the 2 the beginning value, or more generally, why a, the number sitting in front of the exponential function, why this is called the initial or the beginning value. The reason why is that very often this variable represents time, and if you replace this variable with 0, that of course will give you the beginning value of the function, and when you replace x with 0, the b term basically disappears and you're left with a, so you can see that a is the starting value. Or maybe to put it another way, the big idea is that a is the value of the function associated with x equals 0. It's what you get if you replace x with 0. Okay, now why is b called the multiplier? Basically because, with an exponential function, what you're really doing is you're multiplying repeatedly over and over again by some number. And b is that number. if we take again this very same example here, y equals 2 times 3 to the x, if you look at the value of this function for different values of x, you'll see that what you are doing is repeatedly multiplying by 3. So we can just make a small table for this function. So here's x, here's y. I'll start at 0, 1, 2, 3. All right. If you replace x with 0 here, we already know that you get 2. That's the initial value. What if you replace x with 1 in this function? Well, if you replace x with 1, you have 2 times 3 to the 1, which is just 2 times 3, so that's 6. If you replace x with 2, you're going to have 2 times 3 squared. That's 2 times 9, which is 18. And then if you replace, finally, x with 3 in this function, you're going to have 2 times 3 to the third, which is 2 times 27, which is 54. And then what you should hopefully notice between these consecutive y values is that all you're doing to move from one y value to the next is you're multiplying by 3. So from 2 to 6, we're multiplying by 3. From 6 to 18, we're multiplying by 3. From 18 to 54, we're multiplying by 3. And so that's why I call 3 in this case the multiplier. Or more generally, that's why b is the multiplier. It's the number that you're multiplying by over and over again. Okay, as far as graphs, I should show you sort of what a basic exponential function graph looks like. I'm not that worried about graphs, but there's kind of two types of exponential functions. If b is bigger than 1, that's the multiplier, then the graph looks something like this. It sort of blows up as you go to the right and gets larger and larger. As you go to the left, it gets smaller and smaller and approaches the x-axis but never crosses it. This is called exponential growth. So if b is bigger than 1, then you're looking at exponential growth. On the other hand, if b is less than 1, of course b, if you remember, has to be positive. So saying that b is less than 1 really just means that it's between 0 and 1. If b is less than 1, then we have a graph that looks like this. It's kind of the mirror image of the first one. It's actually decreasing like this. And again, as you move to the right, it's approaching the x-axis but never quite reaches it. Anyway, that's called exponential decay. Now, why do the graphs look like this? Not very hard to see. If b is bigger than 1, that's the number that you are repeatedly multiplying by over and over again. So if you're repeatedly multiplying by a number bigger than 1, then the value of your function is going to get bigger and bigger and bigger. On the other hand, if b is between 0 and 1, like if b is a half or a third or something, every time you multiply by that b value, the value of your function decreases. So that's why you see this behavior here. Okay, so let's do a quick example. Very often you see these kinds of problems in textbooks. So here's the example. Find a formula for the exponential function whose table is below. So here are some x and y values. X, y. Let's say when x is 2, y is 7. When x is 3, y is 21. When x is 4, y is 63. Okay, so, these are some x and y values for some exponential function, and we just have to find the formula. Knowing that it is an exponential function means that the function has the form y equals ab to the x. Knowing that it is an exponential function tells us that that is the overall structure and shape of the function. The only thing that we have to do is find the values of a and b. Okay, that's all we have to do. So how do we do that? Well, it's pretty easy if you remember what a and b represent. B is the multiplier, right? It is the number by which you multiply every time to move between consecutive y values. if you look, these y values are consecutive, right? This is the y value associated with 2, and then this is the very next y value, the y value associated with 3. What do you have to multiply by to move between these consecutive y values from 7 to 21, from 21 to 63? Well, you have to multiply by 3. So surely b is equal to 3. Great. Okay, so that's our b value. On the other hand, what is the x value, or what is the value of a, the starting value? It's not totally obvious. That's a little harder to find. Remember that a is the starting value. It is the value associated with x equals 0. Now, we do not have the y value associated with x equals 0, right? But we can find it. Why? Let me just redraw this table a little differently. I'm going to put my x values in a top row, 2, 3, 4, and my y values down below, 7, 21, 63, okay? Now, I want to know the y value associated with x equals 0, right? I don't have it, but I can find it. Here's how. Right before 2, what would the x value be? Obviously 1. And then right before that would be 0. Now I know already that multiplying by 3 moves me to the right. If I want to get from this value to the next value to the right, I just multiply by 3. Well, clearly I can also move to the left. If multiplying by 3 moves you to the right, then how would you move to the left? Well, you would divide by 3. So if I take 7 and divide by 3, that's going to give me this value. And then if I divide by 3 again, I will get the value here, which would be 7 over 9. And so that is the y value associated with x equals 0. That's the starting value. That's my a value. So it follows that a is equal to 7/9. And now I can write down my entire exponential function. It's y equals, well, it's a b to the x. A is 7/9, and then b is 3. So voila, that's the function. Okay, and you can plug in these values to check to make sure that they're right if you like.
Okay, so let's move on to a couple of word problems, which is, I think, really the focus of this section here. So let's start off with an example. So let's suppose that in a bank account, so you've got some bank account, let's say that you, let me turn down the brightness here, this is not looking great. There we go, that's better. So suppose that you've got some bank account and you double your money every, I don't know, let's say 12 years, okay? And let's say that you invest $1,000, okay? And the first thing that I want to do is I just want to write a function, a of t, which gives the amount of money in the account after t years. Okay, so basically what I'm looking for is a mathematical model which tells us how much money is in the account after t years have passed. The first thing I want to do is convince you that this is actually an exponential function, that a of t is actually going to be an exponential function. Now, why is that? Basically, one way of characterizing an exponential function is the following. It is a function where to move between consecutive y values, you multiply by a certain number over and over again. And if you look carefully at the description of the account, it says that every so often you double your money. So what that's telling you is that every so often you are taking the amount of money currently in the account and multiplying by 2. So you're repeatedly multiplying by 2. That is characteristic of an exponential function. If you're repeatedly multiplying by some number, in this case 2, that's an exponential function. Okay, so recognizing that it's an exponential function, here's what we're going to do. I mean, knowing that it's an exponential function tells us that it must have the form y equals a b to the... Now, I could write x here. That would be fine, but since my variable is t, I'm going to use t instead of x. Okay, of course, it's just a choice in notation, but makes it a bit more clear. So this is, just an exponential function. And what I need to do in order to, this is like a template. This is like a prototype of my function. To customize this prototype for this particular problem, in other words, to make this sort of general function match this specific information, I have to find A and I have to find B. If I can find those two values, then I will no longer have a prototype, but rather like a specific function, a specific model for this specific information here. All right, so this is a little trickier than it looks. Let's start with A. So A, of course, is the amount of money or the amount of stuff, whatever it is that you start with, right? It's the initial value. And of course, since you're investing $1,000 at the very beginning, I hope it's clear that the starting value is $1,000. So that's the starting value of the account. So I think it's clear that A is in fact going to be 1,000. That's how much you're starting with. B, of course, is the multiplier. It is the thing by which you are multiplying by over and over again. And since this account repeatedly doubles your money, it's clear that we are multiplying by 2 over and over again. So it would seem like B is 2. Now, if you plug these values into this sort of model, you have y is equal to 1,000 times 2 to the t. I claim that this model is actually wrong. It's not right. It doesn't actually match the information that was given. And you probably want to know why. Like, what's wrong with it? The problem is that, remember the account is only supposed to double your money every 12 years? Yeah, we haven't really used that information yet, have we? So what's going on? What's happening is this model doubles your money, or if you like, multiplies by 2 every single year. Like if I replace t with 1, if I replace t with 1 and plug in t equals 1, then I've got y is equal to 1,000 times 2 to the 1, which is just 2,000. That would indicate that I've doubled my money after just 1 year has passed. But that's not what I wanted. I didn't want to double my money after just 1 year. I only want to double my money every 12 years. That's the information given in the problem. So one way of putting it is that as it's written, this model is multiplying by 2 too often, too frequently. The clock, if you like, is running too quickly and it needs to be slowed down. So instead of multiplying by 2 every single year, which is what this model is currently doing, I only want to multiply by 2 every 12 years. How do you do that? The trick is to actually take this exponent, the t, and divide by 12. So this model is not quite right, but here's the correction that will give us the right answer. I'm going to write 2 raised to the t over 12. Dividing the exponent by 12 basically slows down the clock. This model here will only double your money every 12 years. And if you want to check, it's pretty easy. You know, if this is the right model, then if I replace t with 12, I should get twice the amount that I started with. And that's true. If I replace t with 12, okay, I have y is equal to 1,000 times 2 to the 12 over 12, which of course is 1,000 times 2 to the, well, 12 over 12 is just 1. And as you can see, 1,000 times 2, that's 2,000, which is what I want. So after 12 years have elapsed, I've doubled my money exactly one time, which is what I wanted. So this is an important subtlety to these problems. You have to often modify the exponent to account for the fact that you don't want to double your money or double your stuff every single year or every single day. You only want to do it so often. And dividing the exponent by the appropriate number is the way that you slow down the clock. Okay? So this is the correct model for the problem. If you want to know, that's my A of t. If I want to know how much money is in the account for any time t, I just replace, if I want to know how much money is in the account after 5 years, I just replace t with 5, and I will pop the answer. I'm not going to do that. What I want to do, actually, is ask a related question. So same information, same problem, but I want to add a second part. Here's the question. By what percent does the value of the account increase each year? Okay? This is rather tricky. Now the thing is, we know that the account doubles in value every 12 years. So every 12 years, we know that there is a 100% increase. But that's not what I'm asking about here. Here I'm asking you, what happens in a single year? After 1 year elapses, by what percentage has the value of the account gone up? Let's go back to our model. I'm copying it again here. It was 1,000 times 2 to the t over 12. If you want to know what is happening to the value in the account, not every 12 years, but every individual year, then you have to rewrite this function. Right now, because the exponent is t over 12, this way of writing the function is telling you what's happening every 12 years. It's telling you every 12 years you're multiplying by 2. But I want to know what's happening not every 12 years, but every single year. The trick to doing it is to rewrite this expression so that the exponent is a plain old power of t. Not t over 12 or t over anything else, but just t. All right, if you can rewrite this expression so that the exponent is just t, then the base of that exponent will give you the value by which you're increasing the amount in the account every year. So let's do that. Let's rewrite this function. So you can rewrite this in the following way. First, notice that t over 12 can be rewritten as 1 over 12 times t, of course, right? 1 over 12 times t is the same thing as t over 12. Excuse me. We can rewrite this expression as 1,000 times 2 to the 1/12, all raised to the t. Now you're probably wondering what's going on there. What I'm doing is I'm using the power of a power rule in reverse. Now if you look, what I have here is 2 raised to one thing, raised to another. You know that when that happens, you multiply the two exponents. So you can see that you could use the power of a power rule to rewrite this expression in this form. Power of a power, you multiply the exponents and you get this. But I'm kind of using it backwards. Now, why would I do that? Because this number inside the brackets, 2 to the 1 over 12, because this t is by itself, because the exponent is now a plain old t, that tells us that this number inside the brackets, whatever it is in fact the thing that we are multiplying by every year. Not every 12 years, but every year. So what I'm going to do is just evaluate t raised to the power of 1 over 12. I'm going to type in my calculator here. What is t raised to the power of 1 over 12, it turns out that this number here in brackets is about 1.05946. Okay? So I've just evaluated this expression inside the brackets approximately. So written in this way, we can see, because the t is by itself, every year what we're doing is we're multiplying by this thing right here. Okay? Every year we're multiplying by that expression. Now, here's the question. We want to know by what percentage does the value of the account increase each year. Well, every year you're multiplying by this number. If you multiply by 1.05 blah, 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 what percentage are you increasing the value of the account by? Multiplying by 1.05 is a 5% increase. Okay? So multiplying by 1.05 blah, blah, blah means that every year we are increasing by 5.946%. Okay? So in summary, if you want to know what is happening not every 12 years, but every individual year, the trick is to rewrite the function so that the variable is by itself in the exponent. And the way that you do that is basically by using the power of a power rule. And then you say to yourself, oh, looks like every year I'm multiplying by 1.05 blah, blah, blah. That means that every year I'm increasing the value of the account by 5.946%. And so that's the value by which the account increases every year. Okay, let's do one more example of that type. Okay, so let's do a half-life problem. So these tend to be pretty confusing to students, so I really want to do one. So let's suppose that some radioactive element has a half-life of 5 years, okay? And 2 parts. I want to write a model for the amount of radioactive material after t years. And then the second thing I want to do is I want to find the percent by which the material decays or disappears each year. So just a little bit of background on what all of this half-life stuff is about. So you might remember once upon a time in chemistry or something you studied radioactive decay. Basically, there are certain elements, like I think argon is one of them, maybe uranium, I can't remember, but certain elements decay. And what that means is that they change into a different element. They gradually change into other stuff, okay? And so you've got some radioactive element, which means that gradually this radioactive element is decaying and transforming into something else. So what does it mean to say that the radioactive element has a half-life of 5 years? What that means is that every 5 years, the amount of radioactive stuff gets cut in half. I'll say that again. Every 5 years, the amount of radioactive element left gets cut in half. That tells you that you are looking at an exponential model. Why? Because every so often you're cutting something in half, which means every so often you're multiplying by 1/2. And that is like the defining characteristic of an exponential function. You're repeatedly multiplying by some number, in this case 1/2. So, knowing that I have an exponential model, I can start with my sort of prototype, y equals ab to the t, and all I have to do now is find a and find B, very similar to what I did in the previous problem.
Okay, so the first thing to recognize is that because this problem involves a half-life, what this is telling you is that every 5 years the amount of radioactive material is being cut in half, which means that we're repeatedly multiplying by a half. That sort of tells you that B, your multiplier, should be 1/2, because every so often, in particular every 5 years, you're multiplying by 1/2, and that's the role of B. We don't really know what A is in this problem. A is the initial amount. It would be the amount of radioactive material that we started with. We're not told that information, and we actually don't need it to answer the problem. So all I'm going to do is just sort of take the prototype exponential function here and replace B with 1/2. And that's really as good of a model as we can create without more information about A. Once again, as I've currently written it, this model is wrong, and it's for the same reason as before. Basically, this model is saying take the amount of stuff that you have and multiply it by 1/2 every single year. Because the t is by itself in the exponent, what you're doing is you're multiplying by a half, not every 5 years as we're supposed to be, but actually every single year. Once again, the clock, so to speak, is running too quickly, and we have to slow it down. And the way to do that, as before, is to just divide the exponent by 5. Now, we're no longer multiplying by a half every single year, but rather just every 5 years. And you can check that this makes sense by using some specific values of t. For example, if I use t equals 10, if I plug in t equals 10, I find y is equal to a times 1/2 to the 10 over 5, which is, of course, a times 1/2 squared. So you can see after 10 years, you've multiplied by a half twice, which is what we would expect because the amount of radioactive material is getting cut in half every 5 years. So after 10 years, that's happened twice. Okay, so that's our model. So that's part A. Part B, I want to find the percentage by which the radioactive material decays each year. We know that, the amount of radioactive material is decreasing by 50% every 5 years. Because of this right here, but we want to know not what's happening every 5 years, but rather what is happening every single year. And the situation is just as before. In order to see what's happening every single year, you have to rewrite this exponential expression so that the exponent is just a plain old t, not t divided by 5 or anything else, but just t. And the way we do that is just as we did before. We just have to use the exponent rules to rewrite this expression as a power of a power. So we have y is equal to a times 1/2. And the first observation to make is that t over 5 could be rewritten as just 1/5 times t. And then, of course, we can use the power of a power rule to rewrite this as a times 1/2 raised to the power of 1/5, all raised to the t. You can see that these two expressions are the same because power of a power rule says that, this 1/2 raised to the 1/5 raised to the t, you multiply the exponents, and that would give you exactly what we have right here, 1/5 t. So now the t is by itself inside of an exponent, and what this expression is telling you is that every single year you are multiplying by this expression inside the brackets. And to figure out what that corresponds to as a percentage, we have to evaluate it using a calculator. So I'm just going to quickly ask my calculator what 1/2 raised to the 1/5 power is. 1/2 raised to the 1/5. I get about 0.87. So this is 0.8705. Okay. Right. So and so that's the value of the expression inside of the brackets, and so we have all of that to the t. So what's the lesson here? What we're seeing is that basically now that the t is by itself, this is the expression by which we're multiplying every single year. So every single year we're multiplying by 0.87. The question is the percentage decrease that corresponds to. I mean, if you multiply by 0.87, then a certain amount of the material is going away. Multiplying by 0.87, of course, decreases the amount of material left, since 0.87 is smaller than 1. So the question is, if you multiply by 0.87, by what percentage are you decreasing the amount of material? The answer is actually about 13%. Basically, to figure out how much you're losing, you should take 1 and subtract 0.8705, which is about 0.13. So that's 13%. So, okay. So basically, in summary, these kinds of radioactive decay problems, you know, half-life means the amount of time it takes for the amount of material to get cut in half. And so when you see a half-life problem, you know it's an exponential function because basically every so often you're multiplying by a half, and repeatedly multiplying by the same number does correspond to an exponential function. Knowing that it's an exponential function, you can write down sort of the general formula for an exponential function, and then try and find the specific parameters A and B for this particular problem. In this problem, we didn't have enough information to find what A was, the initial amount. We didn't need it, but we were able to find B by saying, you know what, every so often we're multiplying by a half, so we should let B be a half. But then we said, that's, you know, with the plain old T, you're multiplying by a half every single year. That's not what we want. We only want to do it every 5 years. So you divide by 5, and that's what gives you your model. Okay.